Hi, in this video, we'll be continuing our journey into real numbers and we'll be talking about limits. Before we go into limits, let's talk about this absolute value function because it will act as a distance function for us when we want to do a precise definition of a limit. So what is this absolute value function? Well, it can be defined on any general ordered field because there is a positive. As long as you have an ordered field, you define what is positive and what is negative already. And so the absolute value function is you take a number and you run it through this function and you return the positive value of that number. For example, the absolute value function of 5 is 5, minus 8 is 8. Like how we usually have learned it in our high school. And so some properties of the absolute value function that are important is that it is positive definite, meaning it's always greater than 0, and it only equals to 0 if and only if x equals to 0, and it's quite clear from the definition why that is so. And then it is multiplicative, meaning the absolute value function of x and y equals to absolute function of x times the absolute function value of y. And it satisfies the triangle inequality as well. And so the proof of it is given over here. And really the main idea is that you want to consider the different cases when a and b greater than 0, a and b equals to 0, or both are less than 0, and then you just work it out and you show that this equality holds. For the triangle inequality, we make use of the fact that within any number, it is always bounded by the absolute values from the negative absolute value to the positive absolute value. And you can check that quite fairly simply by, again, using the different cases. So the proof of that, it will be a bit tedious because you need to go through the different cases. But I hope you understand by me explaining the intuition behind the proof. So with that, then the triangle inequality just follows because A is less than mod A and B is less than mod B. And when you add the two inequalities up, so A plus B will be less than or equals to the absolute value of A plus B. And because of that, by what we have said earlier, this means that the absolute value of A plus B is between the absolute value of A plus the absolute value of B. And we're done with proving the triangle inequality. Then there's some corollaries to it, and really it's just rewriting the triangle inequality in a different form. So now we replace the A plus B with A minus B, and then because of that you can just replace it accordingly and you'll see how it follows. So you can prove it yourself and I won't go through it because it's quite simple. So more generally, what we want to say is that this absolute value function works for n elements as well, not just 2 elements. And so the modulus of a1 plus all the way to an is less than or equals to a1 plus all the way to an, each individually. And all these propositions hold in a general ordered field, so you can use them in your complex number as well when you have an absolute value function. And really it acts as a distance because let's now say we have A and B. So B minus A in this case will be positive, but if it's B here and A here, but you still want to calculate B minus A, you just need to take the absolute value function. So you want to know the distance or the length between the 2 points in your real line or in any field. And with that, we'll introduce now what is a sequence and the limit of a sequence. And this really is the starting of what real analysis really is. So for a sequence and its limit, you can work in a general ordered field. Although Shelbert and Bartley works in just the real numbers, we'll diverge with him and introduce some parts where we work in a general order field, and this will really make you understand when do we actually use the real number properties. So a sequence is defined to be a function from the set of natural numbers to the field, or in this case R. because of that, we can enumerate through the natural numbers, making the sequence countable always. So we denote the sequence in this format. So what we really want to say is we have a general sequence, and whether there is such thing as a limit to the sequence. And we say it has a limit, or it converges to this limit x if and only if for every epsilon there will exist a number k such that when n is greater than k, all these xn minus x, the distance between them is less than epsilon. So you can imagine you have a real line here, and your sequence maybe is everything in here, then it gets closer and closer to this value b. So for every epsilon, meaning now b is a smaller distance away from every point in the sequence, but there will still be a cutoff in the sequence k such that all the points here are close to b. And really, we say that this sequence is convergent if it has a limit, and it is divergent if it does not. And the notations are over here for you to read and see. And really, it depends on the choice of epsilon sometimes when you choose this natural number k. Because in a smaller epsilon, you require usually a larger value of a cutoff point. So that, because if you have a smaller distance, then you can think lesser terms are inside. So you have a larger cutoff. So that all the terms at the back is less than epsilon. And what we want to note is that Rudin has pointed out a very good point, is that a convergent sequence depends on the set that we are talking about. For example, the sequence of 1 over n is convergent in the real line, but it fails to converge if it's just the positive real numbers, because 0 is not inside this set of positive real numbers. And so sometimes it can be there leads ambiguity, and you just need to specify where you're convergent at. But most of the time, it's quite clear to the readers. And so with the definition of limits, now we can prove certain properties of limits. And one of them is we will first show that the limit is unique. And so you cannot have two limits of a sequence. And really that works on the idea, because for every epsilon, there will exist a cutoff for the first limit and a cutoff for the second limit. So, and this cutoff, you put it to be epsilon over 2. And so you can apply the triangle inequality to x1 minus x prime minus x double prime, and you realize that x prime minus x double prime is always less than or equals to epsilon. And since epsilon is a general positive number, we can conclude that xi minus x double prime equals to 0, and we're done. So we've proven the uniqueness of the limit. What we want to take note now is that with this definition, it makes it easy to verify whether a proposed value is a limit, but it does not produces the limit. Like, you can't say that you must have a candidate first and then prove that this candidate is a limit. And how do you usually find this candidate is by computation methods that we will see later on, how we prove theorems to help us with this computation method. Or it could be a general sense, then you feel that it will be that limit. For example, the one below. The limit of 1 over n is quite taught in many classes in calculus that it's 0. And so we want to test whether it's 0, and we can do so by proving it using the definition of a limit. So we are given an epsilon greater than 0, and with the Archimedean property, it means that there is a natural number such that anything greater than it, the 1 over n will be less than epsilon. And this really proves the definition, the inequality already. And so we can say that the sequence of 1 over n converges to 0. You can also see the below for another example, but I hope it's clear how we want to use it, because actually you can think of it as a function from the natural numbers to your set, and you already did a lot of limits calculation in calculus. So really real analysis is trying to just prove the theorems in calculus in a more detailed fashion. And so using the definition of a limit shouldn't be too hard. So we know that x is the limit if and only if for all epsilon there exists a cutoff such that anything xn minus x is less than epsilon. So if you want to prove that x is not a limit, it means you need to produce an epsilon such that for all the k's, all the natural numbers, there will exist some guy bigger than your k such that xn minus x is larger or equals to epsilon. So for example, the one below, we have a sequence of 0, 2, 0, 2 all the way. We want to show that it does not converge to 2. Well, we give him the epsilon value equals to 1. Then, no matter what cutoff you choose, you can always choose a larger guy who is even number, such that xn equals to 2. And so xn minus 0 equals to 2, which is greater than 1. And so the inequality doesn't hold for the definition of the limit. And so x is not a limit. But while it's easy to use this definition to prove why x is not a limit, it's hard to say that a sequence doesn't have a limit, because now you need to prove that for all the x's in the field. So a good way is that you can just use a general x, but sometimes the inequality becomes hard to manipulate. So just take note of that. So with that, I've come to the end of sequences and limits of a sequence. I hope you have enjoyed this video, and in the next video we'll be continuing to talk more about limits to better understand the sequence. Thank you for listening, and I'll catch you in the next one. Bye.